Welcome to this extra lecture on the fundamentals of programming. My name's Carol Morgan. I'm an academic here at UNSW, and I've made this presentation to show you one of the next steps you can take in learning to write even better programs. Many of you will have learned programming at school or from your parents, and all of you have had 5 weeks of programming here in Comp 1 511. As part of that, you've probably learned about how to add comments to your code afterwards, so that you'll be able to maintain it later on. In this lecture, I will show you what can happen if you write comments before you write the code of your program, rather than afterwards. Sometimes beforehand comments will turn out to be better than after, because they will tell you what the code has to be, and will, in effect, write the program for you. We'll start with a small programming example, just 3 lines, and you'll have probably written this program many times already. It's swap 2 variables. Here it is. You'll see that I've included a comment already. The line swap values of x and y says what this small program is supposed to do. I've also adopted a certain style of my own where I write assignment statements with the equal sign left adjusted. I do that because I think it makes the program easier to read, and it reduces the risk of the irritating equals or equals error that sometimes can happen in C. Then I've written the 3 assignments one below the other. Should I put comments on those as well? Or would that be too many comments? If I should comment that, what should the comments be? Well, of course, this program is incorrect. So asking now about comments for those 3 lines is too late. Maybe writing the comments first would have helped, even if they were only temporary, like a sort of scaffolding on a building while it's under construction. And mistakes like that one are very easy to make. We all do it. What this lecture will show you is how good comments applied beforehand can reduce errors like that, in many cases stopping them before they happen. Let's fix this one now, anyway. It's irritating to see it just sitting there. And then we will see how small errors in programming can lead to big consequences. One way of finding a bug, unfortunately, is witnessing a disaster firsthand. Let's have a look at one now. It wasn't caused by incorrect variable swap. Instead, it was arithmetic overflow, something that's very easy to overlook.
By the early hours of the morning of the 4th of June, Ariane 5 stood proudly on ELA 3, waiting for the final countdown. No one would sleep much that night. They never did before any launch. The skies opened again, and the tropical rain poured down over the rocket. There were doubts if it would be able to launch the next day. Its prospects looked poor. By the next morning, the forecast had improved slightly. A final decision to go was taken.
10, 9, 8, 7, 6, 5, 4, 3, 2, unité, feu. Allumage. Décollage. Tous les paramètres propulsifs sont normaux et la trajectoire est normale.
37 seconds into the launch, the onboard computers decided 501 was 90 degrees off course. They made an automatic adjustment to the trajectory as the rocket was traveling at the speed of sound. A A well-rehearsed civil defense evacuation began immediately as clouds of toxic fumes enveloped the surrounding area.
Non, non, monsieur, tout droit, tout droit, tout droit, tout droit, monsieur. Non, 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 tout droit, tout droit. Vous allez tout droit, monsieur, il y a un nuage toxique qui arrive, alors circulez.
The ghosts of Europa had returned to haunt the tigers in the jungle. The recuperation and recovery teams were back in action again. The mighty Ariane 5 had been blown to pieces by faulty computer software.
As I said, the Ariane error was not a coding error for swapping two variables, but the actual error was still very simple, and its cost, losing the Ariane and the 4 satellites it was carrying, was over $1 billion in today's money. It could have been detected and prevented by more careful procedures in writing the software in the first place, and of course in testing it afterwards. Here we will learn about some of those procedures. But first, let's just emphasize what happened with the Ariane. How a small mistake, in fact something that nobody thought was worth worrying about, can have such a large effect. The error is small, but it's part of something larger. Testing of the small component on its own, just a swap, might catch the error, but who would bother to test a swap on its own? But testing the larger component might not actually test the swap itself, at least not exhaustively. And when that larger component becomes part of something larger still, again and again, and the bug is buried deeper and deeper, and yet, on the day, out it comes. It's a low probability event, but it has enormous consequences. In the Ariane case, there were several small errors and bad decisions that interacted only when the whole thing was put together. So what's the solution? It is try not to make errors in the first place. But how can we do that? Let's look at the variable swap again. We'll look at a commenting strategy that would have prevented the swap variables error in the first place. Key to that is a certain style of comment, the "what's true here" comment. Let's have a look. Before the 3 statements, variables x and y have some initial values, say capital X and capital Y. That's what's true before. It's a "what's true here" comment at 1. And what should be true afterwards is that the x and the y should be the other way around. That's a "what's true here" comment at 2. Those 2 comments together say, in a particular style, which we will explore, just the same as the English comment swap variables x and y at the front. What's maybe a surprise though, and maybe the first real surprise of this lecture, is that there are sensible "what's true here" comments you can put temporarily in between those statements to check what you're doing as you're going along. Here they are. Each one is a "what's true here" comment. The 1 and 2 summarize what the whole thing is doing. The others help us to see what's true along the way. Those are the ones indicated by arrows. Let's pull the middle before comment, statement, after comment out and have a look at it on its own. There are 3 of those triples altogether in this program. Do we need the rest of the program to see whether this little bit is correct? Here's maybe the second surprise. We do not need the rest of the program to check this. Each separate comment, statement, comment, triple can be checked on its own, and the procedure for doing that is extremely simple. Here it is for an assignment statement. Just do what the assignment statement says, but moving from the after comment to the before comment. Do it for all 3 triples and then glue them together. and finally erase the middle two comments. They were temporary scaffolding that you used while writing the program by following the procedure on the previous slide. But the theme of this lecture is letting the comments write the program, and we will get to that. So far, however, we are still writing the program first and then adding comments that we can check for correctness. But look, already, if we erase the code in between the initial and the final comments, we have all we need to understand what swap does in a larger program, without seeing the code at all. And that procedure generates the comments for the swap as a whole. And that is the big message, at least so far. The what's true here comments that we are advocating have two key properties. The first one is that you can use them alone without looking at the code, looking outwards to see whether the component is correctly placed in a larger structure. And the second thing is that you can look at the component's comments and code in isolation, looking inwards to see whether the component is correctly programmed without looking at the larger structure that it eventually will be embedded into. If you're the one who uses a function, you need to know only what it achieves, not how it does it. If you're the one who wrote the function, you need to know how to make it do what its exterior comments say, irrespective of who might be using it and for what. You could, of course, be both people on different days, for now. Later, it will be different. We'll now look at a second example. We have three variables x, y, and z, and we want to rearrange them so that they are in ascending order. This time we will write the comments first. The braces xyz equals capital XYZ is just to say that the three variables collectively must not change. So you can't just assign 0 to all of them. And this time we introduce the code and the comments at the same time. Remember that order swaps its arguments if necessary to make the first one the smaller of the two. So we are progressing. First it was code alone, then it was code with comments added afterwards. Here it is comments and code done together, and later on we will indeed do comments first, then code. This gradual style is part of the teaching process, how I teach you and later how you will teach yourselves, which is what practice is. Now let's look at the steps in detail, focusing on the second one, order xz. It's not quite as simple as the swapping example we had before. For example, how do we know that x is less than or equal to y is still true afterwards, given that the statement order xz could have changed x? The x is less than or equal to z is not a problem, because that's what order xz's comments tell us it will do. Informal, but still local reasoning gives the answer. If order xz does change x, it can only make it smaller. So x is less than or equal to y remains true even if x changes. If we try the same strategy with 4 variables instead of 3, it still works. What about with 5 or with 6? Is this getting out of hand? How can we do this generally? To do this generally, we use an array, of course. You can see the W, X, Y, Z pattern on the right, but with numbers rather than names. The program looks a bit like bubble sort, but it isn't quite. It is not insertion sort either, but it is a variation on those themes. We will come back to it later. First, before we deal with arrays, we need to think about comments for loops in general. So now we'll look at a commenting strategy that would have prevented the swap variables error. Key to that is a certain style of comment. The what's true here comment. Let's have a look. In this course's lectures, week 3 in term 1 for example, there were some remarks about how many iterations does this loop carry out. Let's see whether comments can help with that. Your first reaction is probably to run the loop in your head and count the iterations. It's mine too, actually. So we go 0, 1, 2, all the way up to 9, counting as we go to get 10 iterations for the first one. If we notice that we started at 0 and ended at 9, there's a tiny little extra thought that was necessary for that. The second loop seems much more straightforward. Here you can just count it on your fingers, and you have 10 of those, right? The third, however, well, the third loop is a bit odd, deliberately tricky. You have to have noticed the less than in order to stop at the right place. That's not a problem here if you're keeping alert, and especially since you know these are little puzzles and you are on your guard. But if you're tired and there are lots of these, well, let's see now how comments can help. Here are all three programs again. What would be a good "what's true here" comment for the first loop? It is, of course, done n iterations. When n is 0, you've done no iterations. When the loop exits, you know n is 10, just look at the loop condition, and so you've done 10 iterations. Important, this conclusion is reached without any counting at all. You do not need your fingers to figure this out. Now the second loop. When n is 1, you've done n minus 1 equals 0 iterations. When the loop exits, you know n is 11, look at the loop condition again, and so you've done 11 minus 1 equals 10 iterations. And now the third loop. When n is 1, you've done n minus 1 equals 0 iterations, as for the second loop. But here, when the loop exits, you know n is 10, look at the loop condition, and so you've done 10 minus 1 equals 9 iterations. But do these differing loop comments make any difference to the code quality? Actually, they do. The code for the second loop is not wrong, but it is dangerous. Does dangerous matter? Yes. Small dangers combine to make big disasters. And here's another look at the third loop. It's bad style. Indeed, the code works, if 9 iterations is what you want, but someone in a hurry could easily think, with a quick glance, that there are 10 iterations. In fact, the first loop had the best comment, there were no n minus 1s in it, and it gives good code style as a result. So, going backwards while you're still learning, if you want to check for good coding style, put some "what's true here" comments into your program and see whether they are as simple as possible. So the message is that, in programming at least, good style is actually not just a matter of opinion. It's not a matter of beauty or fashion. It's a matter of science. Comments must inform, of course, but the "what's true here" comments should be as simple as you can possibly make them, even if you don't write them explicitly in your program. They are still there, invisibly between the lines. And, as we will soon see, they can help you to write the program. Here, for example, they give us the initialization and the loop condition for free. That is, get the comment right, and the rest will follow. Next, we will look at some more substantial "what's true here" comments for loops, ones that contribute to the loop body as well. So let's get started with "what's true here" comments for loops, and in particular loop bodies. We'll use as a simple example this program, which is supposed to raise base b to the exponent e and put the result in p for power. But actually this is not a very good program. It multiplies by b once too often. It's an easy mistake to make, though. It's also easily caught by testing, since it's wrong every time, unless b is 1. One way to fix it is to change the loop condition, like this. There, that's better. Or maybe not. In fact, the mistake made here is not the one we discussed on the previous slide. Instead, it's that when we ran the previous program and it said base 2 to the power 2 is 8, our reaction was just to edit in the obvious fix. The mistake we've made here is to slap in a quick fix and hope that everything will be fine. Our reaction should have been, maybe I should have used a "what's true here" comment in the first place. For this program, unfortunately, base 2 to the power 0 turns out to be 2. And that's not so easily discovered by testing. Would you bother to test the e equals 0 case? Well, you might, but there are plenty of people who might not. Why would anyone want to use a program to raise a base to the power 0? You don't need a computer for that. But a computer might do that because the surrounding code is not human. That is, we might not need a computer to raise something to the power 0, but this rocket might. So let's start from the simplest, most obvious "what's true here" comment you can think of and let it write the program for you. In this case, a good choice is p equals b to the n. Let's stick that "what's true here" comment in as the loop invariant. Now what? The first thing that comment does is to tell us how to initialize p and n, and we don't have to look at the loop body or the loop guard to do that. Then that comment tells us what the loop condition should be, and we don't need to look at the initialization or at the loop body to do that. We can now already see that the answer will be correct. Here's that step. All that's left is the loop body. It must respect the loop comment, that is to say, the loop invariant. What does that mean? The loop body has to respect the loop comment in the sense that if the comment is true here at the beginning of the loop body, it is also true at its end. We will do that in 2 steps, and here is the first one. And here is the second. Now that does generate a lot of comments. You need not include them all in your program, since once they have generated the program, you can often regenerate the comments by working backwards through the code from the important ones. And you can certainly have too much comment clutter. If we remove all this scaffolding, we will be left with just this, the loop comment. It suffices for simple loops. Usually, it's enough on its own. With all that preparation, identifying and giving examples of loop comments will now get serious. Let's sort an array into ascending order. We saw earlier examples of this with the XYZ and the WXYZ examples, and it suggested a pattern. Start with the first one in alphabetical order and order it with respect to all the later ones. Then start again with the second in alphabetical order and order it with respect to all the later ones, and so on. Can we make a program from that? Sure, why not? Generalizing that pattern to an array would look like this. And now all we have to do is to write 2 loops, one inside the other, that follow that pattern. That gives this, which is pretty clear. Experiment with the WXYZ, then generalize, as it right on this slide, and capture in some code, as on the left. Note that the code has a "what's true here" comment at its end. Doing it this way is okay, especially when you're still learning. The outer loops construction is clear from the left-hand indices, and the inner loops construction is clear from the right-hand indices. But given what we're doing here, we should still be interested in how we could check the correctness of this obvious algorithm. Actually, it's obvious in outline, but the details of where the i's and the j's start and stop are a bit tricky. We're using, by the way, I:(j) to mean from I up to just before j. Here, very quickly, is a glimpse of what a foolproof would look like. It's surprisingly detailed, and we will not look at those details very carefully. What it tells you, though, is that sorting algorithms are actually more complicated than you might think. This one, however, is okay. I have not inserted a deliberate error this time. So first, the for loops j++ generates an invisible j++ at the end of the loop body. And the inner loop body respects the inner loop comment. This tells us, with a comment, what the inner loop actually does. It makes ai the smallest element in the suffix of a from I to the end. And that tells us that the outer loop body, which is in fact the inner loop, respects the outer loop's comment, which is that the I-length prefix of the array, that is a up to just before I, is all in its final positions. Remember that 0:i is 0, 1, 2 up to I-1. And here again we have to take account of the invisible increment, this time of I. And now it's just a matter of using the outer loop's loop condition. And the whole thing is done. That does seem like a lot of work, and it is, especially for such a small program. But there are compilers for C-like languages and others that will do all this for you. It's quite amazing. Unfortunately, in Comp 1511, you will have to keep using your neurons for a while. And now finally we get to the real example of the comments writing the program for you. And now we're on the home stretch. We're going to look at an example of where we really do let the comments write the program before our very eyes. This will be our example of where we really do let the comments write the program. Bubble sort. Bubble sort bubbles high elements up to the end of the array where they get stuck below all the other elements that were bubbled up already and hence are greater, until finally the whole array is filled with properly sorted elements from top to bottom. The two comments describe that. For the outer loop, a suffix is final, things in their final positions, and for the inner loop, the maximum is at the end. All the question marks here indicate material that will be filled in for us by the comments. All that includes the inner loop body, that is, which two elements should be compared. Here we go. Watch how the comments write the code. The first step is to translate the "what does this do" comment, which is still necessary by the way, into a "what's true here" comment at the end of the code. Note that here already we have noticed that it's enough for A1 up to n to be in final positions, because that implies that A0 is in its final position as well. And we notice it now rather than later when we're wondering what the outer loop for condition should be. Now we compare the outer loop comment with the final comment, and we see that at the end I must be 1. That writes our outer loop condition for us. The outer loop initialization comes from making sure the outer loop comment is true initially. It's true if we set I to big N, because then the array suffix a n to n is empty, and so all elements in there aren't any, are in their final positions. Now we can see that I starts at capital N and has to get down to below 1. So we need a decrement I statement, that is I minus minus. And that's the outer loop done. For the inner loop, our first step is to decide what it must do in order to respect the outer loop comment. If the array ai up to n is in final position and ai minus 1 is the biggest in the prefix, then we can decrease I. That gives us what the inner loop must establish. And that, in turn, gives us the inner loop condition j is less than I minus 1, because j must equal I minus 1 at the end of the inner loop. The initialization is determined by making I0:j empty, and the increment j++ is determined by having to move j from 0 to I minus 1. And the order statement, therefore, must compare aj with the next higher aj+1. And we are done. Even if you don't follow this process in detail, and in the beginning you will want to do it only here and there, it will still improve the quality of the code you write. It's more likely to be correct, and you have already documented it as you go along. So do we need to test these programs? The answer to the question posed here is 2 to the power 62 if you take commutativity of addition into account and you test only and all the x's and y's that don't overflow, which at 1 test per nanosecond is still considerably more than 100,000 years. So is testing necessary? Is it really? Is it really necessary? Yes, it is. But why is it? Here's an example of where testing was necessary. I coded up and tested all the programs used in this presentation. And here's what happened with the first run of bubble sort. Look at the bottom left of this slide. The problem was that I had taken the code for the earlier sort and edited the for loop portions, but I had forgotten to change the order statement. So that's basically all of it. What's in it for you, though? If we have to do testing, what's the point of all of this? What can you take away from this presentation? What you have just seen is more advanced than what you are currently doing, and you do not need to apply it right now or even anytime soon. It's not examinable in any case. But to become really good programmers, in the end, you need to know that this stuff exists and that it is essential to writing programs that you really understand and that you can have confidence in. Nearly 50 years of experience has shown that executing the program in your head is not enough. You will get better and better, but the more programs you write, the more ambitious you become. How do you stop your coding adventures from getting beyond what you can understand and control? Do programs actually have meanings? Yes, they do. It's one of the most famous computer science papers of all time, assigning meanings to programs. Google it and have a look. What's true here comments are the key. They were invented in that paper. Try to use them alongside your normal comments. Take advantage of half a century's worth of experience. And how do you learn to write rather than simply appreciate these what's true here comments? Well, it takes practice. Practice by programming in your usual style and then, now and then, try to figure out a what's true here comment that would be useful in some loop that you're especially proud of. Do it a lot. Practice. See whether you can write better and better what's true comments as your experience increases. Try to write better comments than your friends. Go up a level. And just to drive the point home, finally, here's bubble sort again. Unfortunately, bubble sort never really goes away. It will keep popping up throughout your entire careers. We wrote this program from its what's true here comments. And here is the pattern its indices follow. Remember that for our first sorting program, we used the pattern to write the program. For this program, instead, the comments ultimately generated the pattern. I did not type that pattern in. I got the already written program to write it out. That is, I made the program show me what it was doing. It was already correct. I didn't use what I thought the program should be doing to write the code. I went precisely the other way, from comments to program to execution pattern. The last, as above, just to double check that all seems reasonable. Here are some small exercises for you. They're not homework, you don't have to hand them in. In these exercises, you should use the supplied loop comments to generate the program code that's missing. So that's it. I hope you enjoyed listening to that and that you will find it to some extent useful. Just remember